So if you want to substitute the hydroxide with the nucleophile, the trick needs to be played. So what is the trick? Make that oxygen as a part of the good living groups. That's the where we talked about is tosylate. Very strange named molecule, but that is just nothing but sulfonate. And then it has a lot of different things connected to it. The most famous one, the popular one, is a para-toluene sulfonyl groups. So that is something we also call as a tosylate. So that's a tosylate as a middle groups. I mean, you can have a methyl groups there, that's a methylate. You can have a tricyclic methyl groups there, there's a tripolate. There's all sort of variants there, but the main thing is a sulfonate aspect, like this aspect there. So if you have a nucleophile, like a cyanide, which is an absolutely good nucleophile, that attack this carbon, but not the other carbon, because they don't have electric deficiency there, right? This carbon is the one that is electric deficient because of the oxygen being there. So don't try to make this attack to other carbon, because they don't get invited. Only places the nucleophile can go after is electric deficient carbon, that's this one. So it makes an attack there, but it has to take out the whole thing. This whole thing has to come out. But that makes an anion right there, right? Sulfonate anion. If that's what it is, just without any making a resonance structure, then it's impossible. But we know that it makes two other resonance structures, making other oxygens carrying charges. So each oxygen has to have like a 1/3. All of three are equal contributors, right? They're kind of equivalent. So that's the reason why the sulfonate becomes a very good living groups. Because of that, you can pick out this whole thing as a living group, and by making a nucleophile attack that carbon. So we get the substitution done. So this is kind of a trick that we play, and I want to know what the sulfonate, so what's a tosylate, what is that for, and how it can be used. So for instance, and then we're going to talk about, you probably talk about how you're going to make it. The sulfonyl, the tosylate ester can be created from the tosyl chloride, and chlorine is the one that gets replaced by the hydroxyl groups of the alcohol. So we got alcohol here, and then the pyridine is down here, this is the base. It just takes the protons away to make the reaction moves back. But anyway, right now, you don't need to consider about what the tosyl chloride is doing. Oxygen is going to replace the chlorine, sort of a similar manner that we talked about in substitution reactions. It is not, but right now, you can simply just assume that that would say assumption if we talk about the detail later. But anyway, so our hydroxyl groups, oxygen of the alcohol, will replace the chlorine, so it makes a sulfonate and tosylate. And then obviously by the process, you're releasing HCl. So that's the reason why we put the pyridine to neutralize HCl produced by the reactions. But that doesn't really concern right now. But that's how you create a tosylate. And then the next step is cyanide, making an attack, take this whole thing into living groups. That's the way you can make the oxygen goes away as a part of the good living groups. You cannot directly attack the cyanide to the hydroxyl. That is something that you want to do. I'm pretty sure that everybody wants to do. If I'm asking you, you got the alcohol, you need to change this to the cyanide, then somehow you may remember that cyanide is a really good nucleophile. Sure, this maybe that's a two reaction question because I see cyanide plays in the position of the hydroxyl groups. So it just make an attack and then we just kick the hydroxyl groups out. It sounds really reasonable on paper. I mean, time machines are reasonable things on paper too. So there's a lot of things make sense when you dream about it, but that's not possible because we talked about the reason why it doesn't happen. Hydroxide is a really bad living group. They don't want to live. That's the thing. So the trick is you have to make oxygens a part of the living groups. That's what this first part is doing. Number one is almost like a cooking instruction. When you want to eat a pasta for the dinner, you shoot a dry pasta, you drink the hot water, and then you eat the tomato and drop it up and down, so it's like the pasta made you stomach. You don't do that way, right? Step one, you have to boil the pasta in water. Step two, step three, so this is a step. First step is treating the alcohol with sulfonyl chloride, so you get the tosylate prepared. This is number one means the steps. And then after you prepare that, you treat that with the sodium cyanide, these reactions. So you actually make that catalyst one and kick the whole things out. So we get the substitution of the hydroxyl groups of the alcohol with the nucleophile. But something has to play in between, and that is making tosylate. That's the kind of a trick you can play to make the hydroxyl go as a living group, not by itself, but as a part of the living group, like tosylate. So this is something that you really want to know. I've been talking about this process also because of, not because of bromide is a bad nucleophile. I mean, bromide is not a superb nucleophile, but it has a good nucleophility. I would consider it as a moderate nucleophile. It's not because of that. It's not because of the carbon didn't lose electronegativity to the whatever it bound to, oxygen, the second highest electronegative atom. It has a capability of the pull density from the carbon, make this carbon vulnerable to the nuclear head. But why this thing doesn't go? It's because the hydroxide is a bad living group. That's the thing. And that's the reason we've been talking about converting these hydroxyl groups as a part of the living group like the tosylate and then make them live together, right? That's the what we just talked about. But there are other ways. What it is, using acid. Proton, it can be given by acid like HCl, HBr, other type of acid. We like to use like HBr. If you're using HBr, proton will be given to the hydroxyl group because it's a lone pair. It makes a protonated alcohol, and that is basically the water sitting on the carbon. That's the what it is. If you get the protonation done to this oxygen, bromides hang around and they see that, oh, this is ready now. If the bromide kick this carbon, what gets released? Neutral water. So that's the one I said. Third class of the living group is a neutral molecule. You can kick out the neutral water by adding HBr to the alcohol. Still, you need to have a good living group. Tosylate before is an anion, but it's a stable anion. But this time, we're going to make the OH go out as a part of the water, neutral water. So this is a trick. You put HBr to the solutions, then hydroxyl groups get protonated. It becomes oxonium ion, like a water sitting on the carbon. Now the attack happens, and then you release the water. So that's why this actually goes well. So this is something that you could do to substitute that. So after seeing these things, you get very creative ideas. And I do get the what I'm going to show you here a lot. So let me tell you why this thing is trouble. So basically, the task given is you want to make this from that. And then you see there's a methyl groups sitting on the oxygens. And then so far, we only been discussed about the substitution reactions. So you probably think that I like to substitute this OH with that. Right? So that's basically what you want to do. Well, you may use a tosylate, but somehow we forgot about that. And somehow you remember that I can probably add an acid, make the OH as a water, like oxonium ion there. So if you have a nucleophile with the oxide there, it makes an attack and kick the waters out, then I can make this. Very sound proposals. And then it almost looked like what we just talked about in the previous slide. So let me remind you what it was in the previous slide. We have a methanol there. You put an acid, so you make oxonium ion right here. And then nucleophile, like a bromide, makes an attack, kick the waters out, so we get a substitution reaction. which is almost same as what I just pointed out here. You protonate the alcohol, so you get the sodium ion produced right here. You combine, makes an attack, take this thing out, you get the product form. Same, right? So this looks like a very nice process, but I'm going to say that doesn't work. It never works. How many times you're going to try it, I can guarantee you will never get this thing done. So what is the problem there? It's almost identical, except that I changed the Br minus with another nucleophile, like the methoxide. So what is the problem here is bromide is not a good base, right? HBr, they deionize really easily. That makes HBr really strong acid. I mean, it is strong acid. HBr is actually the most strong acid than HCl. Hydrochloric acid, how would you drink? You drink it because then you will die. Hydrobromic acid even stronger. So that's something that bromide doesn't want to be associated with the proton. They just hate each other, they dispose away. On the other hand, this is a strong base. When strong base see an acid, it pick up the proton instead of the main peptide. What is the fastest reaction people found is actually acid-base neutralization reaction. It takes I forgot I was studying. It takes a little, it's a femtosecond. It was the fastest reaction is base grabbing the proton seems to be the most fast reactions people can study. So if you want this base or nucleophile, attack this carbon, but the thing is that this is not a good nucleophile, it's also a good base. So you can actually pick up the proton a lot faster. So that's what happened. This gets a proton, and then it becomes an alcohol. Once it becomes an alcohol, then it's not a good nucleophile. No acetylation can happen, and then alcohol doesn't get protonated at all. So this mixture is basically you're forgetting the reality of these things. Now, when you're good nucleophile, almost with a good base. So that's the reason why this process doesn't go. You just thought that you may be able to use that HBr to doing this chemistry, the same thing. HBr protonate the hydroxyl groups, make this, bromide attack that, and then release the water, and you get the substitution done. So why this one's done, why that's not? Because of Br minus, that is not base. That simple fact makes this impossible. This one's not possible because that's basing at the same time as against nucleophile. So do not try to use this process for everything. This process has a limitation. Whatever the nucleophile you're going to use with an acid has to be not basic. Right? If it's a basic, it'll just pick up the proton. This process will not happen. So that's why the twisted is actually the better way because it will happen, because you just make it and you just react with the nucleophile. So there's a less exception. This one, whatever the things that you're going to use, that has to be not basic. So, but once you produce that, now it has a bromide there, so you can have a methoxide using the nucleophile. The second step, that's where I said this can be the multi-step reaction, not a single step. Then you can have the substitute by the SN2 reaction, you can produce it. But if you're trying to find a shortcut by just adding an acid and then directly put this base to it, no, it won't work. On paper, yeah, sure. So that's the things I'm going to tell you. This process, really nice, but it is a limitation. So do not try to use it blindly for everything.